Here is a matrix with 3 columns. We can think of each column as a 3-dimensional vector. The red vector points in the x direction, the green vector points in the y direction, and the blue vector has both x and y components. These 3 vectors are special because they are linearly dependent. Another way to say this is that they are coplanar. We can see that all 3 lie in the same plane. This means that we can use any 2 of the vectors to make the third one. In fact, we can reach any point in the xy plane using only these vectors, so we say that they span the xy plane. Because these vectors are the columns of the matrix, we also call this the column space of the matrix. But we can't use any combination of the 3 vectors to reach a point outside the plane, because none of them stick out in the z direction, even a little bit. Even though these are 3-dimensional vectors, they only span 2 dimensions, so we say that the matrix has rank 2. The rank of the matrix could have been 3 if the columns were linearly independent, but because the matrix has more columns than its rank, we say that the matrix is rank deficient. Here's the same matrix with the third column slightly changed. It now has a tiny component in the z direction. Now the 3 columns are linearly independent. In other words, we can see that the third vector sticks out from the plane, although only slightly. This also means that we can combine the vectors to reach any point in the 3-dimensional space, although we might need lots of copies of the blue vector to reach points with a large z value, because its z component is so small. Therefore, the column space of this matrix is all 3 dimensions. Technically, the matrix has rank 3, and it is a full rank matrix. It is no longer rank deficient. However, as we noted, these vectors are just barely linearly independent. The third one sticks out only slightly. You could say that this matrix is nearly rank deficient. This can be a problem when doing calculations on a computer because computers can't represent numbers exactly. They make rounding errors and can have trouble telling apart numbers that are almost the same. Therefore, it can be dangerous to do calculations with a matrix that is nearly rank deficient. You might think that the matrix has full rank, but it is so close to being rank deficient that the difference can be lost when the computer makes rounding errors. Here is another version of the same matrix where the blue vector is completely independent from the other 2. Because the blue vector doesn't point even the slightest bit in the directions of the red and green vectors, we say that it is orthogonal to both of them. In fact, in this matrix, each vector is orthogonal to the other 2. We call this an orthogonal matrix. This matrix is very safe to do calculations with. In simple terms, the computer isn't likely to confuse the directions of the vectors when it makes rounding errors. We have a measure called the condition number of a matrix that tells how risky it is to do calculations with that matrix. The higher the condition number, the more risky the matrix. The condition number of this orthogonal matrix is 1, which is considered a good condition number. The condition number of the previous matrix, the one that was nearly rank deficient, is about 30, indicating that it is much more likely that rounding errors will cause problems when using it to do calculations.